You can start.
Thank you, Lydia. Yeah, I'm taking the opportunity to present part of my work to you because I haven't done even to many of people here at the Institute. And I will be, I think, in a sense, a bit broad on presenting my work. But then you can ask me at the end if you want more specific, to be more specific on some of the topics. Because what I do, again, in general, is studying star formation at subgalactic scales and across different redshifts. So how intended this presentation is like a voyage across redshift to study star formation. And of course, we will start from redshift 0. And in particular from this galaxy, which is not a real galaxy. So I asked ChatGPT to produce this galaxy. And the reason why is that I also asked ChatGPT to produce a second galaxy, which should be the same, but I also added a specific instruction. I don't know if any of you want to guess what's the specific instruction. For the sake of time, I will tell. But I think it almost nailed it down. But I asked to produce the same galaxy, but distributing the stars. I mean, making like the stars within the galaxy are distributed randomly. And I think more or less it managed, in the sense, what we see in the right galaxy is more like diffuse light and a lack of stellar structure. So we see some bright points, but here we clearly see star-forming regions. And it may look like a very tiny detail, but I think it's very important, and we'll see why. So this actually is a real galaxy, a nearby galaxy, and we do see that stars are distributed in groups and cluster of clusters. And we know that this is due to the parental gas being distributed hierarchically. So this is orange here is ALMA tracing the molecular gas. And at the very bottom, so the smallest scales of this hierarchy, we have star clusters. And just a few main key points about star clusters. So in terms of sizes, masses, usual sizes, radii of clusters are between 1 and 10 parsecs, and masses, let's say, above 10 to the 3. Smaller, they also are called groups. And because they are so massive, they contain lots of massive stars. And because they contain a lot of massive stars, they produce feedback. And stellar feedback, it's important, first of all, to sustain the star formation cycle. So they regulate star formation, because at some point, gas is collapsing, but feedback stops it from collapsing, and it warms it, and then the cycle restarts. And this may be only, let's say, on the surrounding of on their surrounding, but actually they can have even a larger impact on the galaxy. And this is true, especially in starburst galaxy. So this, for example, is the M82 galaxy, which has galactic outflows. And they are actually powered also by very many clusters at the center of the galaxy. Or in dwarfs that are smaller and lower mass galaxies. And so the impact of a single cluster is larger. This, for example, is well, I put it very tiny. Now we'll see why. Is ISO 338, a nearby star-forming dwarf. And what happens is that the cluster within the dwarfs are able to produce this very large ionized gas around it, where also there are channels of high ionization, which here is the light, like yellowish part. So the takeaway point here is that actually they can have even galactic scale effects, even such small structure. And on the other way around, they can be affected by their environment. So this is the cluster mass function. This is in M51, so another nearby galaxy. Cluster mass functions is the distribution of the number of clusters per mass in the galaxy. That means that since it's the declining power law, it means that there are a lot of low mass clusters and very few high mass clusters. And not only this is actually not a real power law, but it's deviating, such as it's truncated at the high mass end. So there is a cutoff mass that more or less sets how massive can be a cluster within a galaxy. And it looks like this cutoff mass correlates with the properties of the galaxy. So on the x-axis in this right plot, we have the star formation rate surface density of the galaxy, which, if we think about the Koenig-Smith relation, it correlates with the gas surface density. And it looks like in denser galaxies, denser galaxies are able to produce more massive clusters. And not only, well, here I put to give an idea. So at the high mass end, at the high density end here, we have starburst. At the low density here, we have this Andromeda. And the same correlation is seen in terms of cluster formation efficiency, which basically is how much of the current star formation takes place in bound stellar clusters. And again, we see that in denser galaxy, most of the star formation is concentrated in clusters. So lines here are actually not fit, but they are models. And compared to the previous relation, there's much more scatter here. It's much more complicated, but it looks like there's a trend. And again, so we have starburst here and here low density galaxies. I wanted to mention a few open questions, which I think is interesting in this regard. And one is about dwarf galaxies, because it's been noted recently that it is the same plot as before. And again, on the x-axis, star formation rate density of the galaxies. It looks like in some cases, dwarf galaxies have very high star formation, cluster formation efficiency. So they actually form, even if they are low density, a lot of mass within clusters. So both in these two studies. So it's not clear if it's true that star formation can be very much clustered also in dwarfs or not, and if very massive cluster can be formed in dwarfs, and under which circumstances. And in that regard, there's an ongoing project with JWST observation, in which we are trying to study very low density nearby galaxies, trying to see if we can find massive clusters. And another interesting question is about the feedback timescales, because both according to simulation and observation, it looks like it's very fast, the process of clearing a cluster from its natal gas. According to simulation, even less than 4 million years, so even before the first supernova are appearing. And also observation there are lots of more uncertainties. It looks like it's between 4 and 6, so it's there where we expect the first supernova to be. And this is important because if this time scale is short, it means that when the supernova are exploding, they're exploding in a gas-free medium. So their energy can be just will have an impact on the entire ISM and not only on their gas clouds. And again, even here there are new projects, especially with James Webb, in particular FANGS, but also FIST, that are aiming to observe the embedded phase of star formation in nearby galaxies. Now, a lot more could be said about nearby clusters. I choose to focus on these few aspects. The key takeaway point, I think, may be that star cluster can affect the environment and vice versa. They are affected in their formation by where they reside. Now, we can move to higher redshift, and I want to make a quick stop at cosmic noon. Because cosmic noon, I think it's very important. So here, the black curve here is star formation rate volume density across redshift. So we know that cosmic noon is where most of the star formation in galaxies took place. And the problem is that if we go away from nearby galaxies, as soon as we go away, we lose the resolution, the physical resolution into C clusters. So we don't see anymore in clusters. And actually, what happened with JWST is that looking at galaxies at cosmic noon, galaxies seem to be dominated by the presence of these bright clumps that we see in the galaxies I'm showing here. And in particular, this blue curve in the plot is the fraction of clumpy galaxies. So how many galaxies have at least one very bright UV clump? And it looks that it more or less follows the star formation rate density curve. So that the increase of star formation in general, the star formation process is related to the production of these clumps. That because they're at cosmic noon, because it's JWST, they have the resolution of 1 kiloparsec, so they are very large scale. They are very large star forming regions. And the idea is that the production of these massive clumps is because these galaxies are gas-rich and turbulent. I won't go into the detail of this. But so what we can do, and here's the point about gravitational lensing, is that thanks to lensing, we can try to resolve smaller scales in this kind of galaxy. And what we see in particular is that these kiloparsec clumps are not really monolithic structures. So they're either smaller or they contain smaller substructures. What I'm showing here in this bit crowded plot, effective radii of star-forming regions versus the UV luminosity. I'm comparing what is seen at zero redshift. So these, the contours here, and here is like the median. These are local H2 regions, while all the other points that more or less stays in this band, these are redshift, I mean, star-forming region at redshift between 1 and 2.5. We are not reaching, again, the scales of individual clusters, because here the smallest is 10 parsec. So they are mostly between, let's say, 10 and 100 or 1,000. But it looks like if you convert this UV magnitude into star formation rate, it looks like these at redshift 1 or at redshift at cosmic noon, let's say, star forming region are denser or have a denser star formation than locally. And this, I think, can be mainly due to two reasons. So either their parent clouds, so the gas clouds, also are denser than what is seen locally, or then the gas clouds are the same, but they are more efficient in forming stars. So we know that locally star formation is inefficient, maybe at cosmic noon is more efficient. And luckily, we got the observation of molecular gas in the same lensed galaxies at redshift 1. So the problem is that we only have very few examples. These are two examples at redshift 1. And what happens when studying the properties of these gas clouds is that it looks like also the gas clouds, which here are the colored process, and here it's a size mass plot. So they are denser than their local counterpart, which are the gray points here. The problem is that we don't have like a real statistical sample. So this is based on only two galaxies, but it looks like the parent gas is also denser at cosmic noon. And doing the comparison between the gas clouds here and the cluster, it looks like there's also, it looks like it's more efficient. So that efficiency in converting gas to stars can be as high as 10, even 30%. Again, the sample is very small. Luckily, there are James Webb program about this galaxy that will help us at least trying to better constrain this conversion, so the efficiency of converting gas into stars in this galaxy. But here the problem is that we really need a larger sample that currently is lacking, and it's very difficult to gather in terms of data. Okay, so after the stop at redshift 2, we can get to all the redshift we can reach. So we have now a lot of lens system. So starting from, let's say, 2010, 12, there's been individual study of highly magnified galaxies, tens of them, let's say. And in a recent work of last year, I tried to collect all of these studies. And again, it was like 10, 30 galaxies, or a few hundred of clumps, of lens clumps. But now with James Webb is like a statistical machine in that sense, because observing one single galaxy cluster, it can, it gives us the possibility of studying hundreds of clumpy galaxies, and so like thousands of clumps. And these are two clusters where we did this kind of study, led by Adelaide Claesen at Stockholm University. And again, what we saw, is that, again, if you compare what we see in our redshift galaxy to what we see locally, the clumps we see at our redshift are denser, at least in terms of star formation rate, both here and here. And it also looked like there is a redshift evolution. So here, the color of the points is related to the redshift. But beware that here a big problem is completeness. So going at higher and higher redshift are more and more incomplete, so we only see the very bright ones. But now if we look at the stellar mass surface density, so this is not anymore the star formation rate density, we see that the redshift evolution is not so clear. So first being here, the left plot is actually nearby star clusters, and this is their distribution of their density distribution. On average, 10 to the 2, 10 to the 3 solar masses per passage square. And we see that already at redshift 1, 1.5, we are reaching quite consistently 10 to the 3, 10 to the 4 solar masses per passage square. But then it looks like it flattens. There is not a real evolution. So the last point here is actually driven by just one clamp. So, and in the left plot, what I'm showing is actually clamps below 20 parsec scale. So they are almost clusters, or some of them may be individual clusters. So we're really comparing apples to apples here. So for some reason, whatever the process that managed to produce this dense cluster redshift 1, then is this, it looks like it's the same at all redshift then. And it's the same for the right plot, but here in the right plot, density are lower because here we're including also larger clamps. So on average, the density are lower. But again, this redshift 1 to redshift 5, it doesn't look there's a redshift evolution of this of the density of these clamps. Now, again, this is work in progress, and we're doing many interesting tests on this statistical sample, but I also wanted to focus the attention on few individual cases, which I think they're very important because it's where in our redshift galaxy, we're really managing to see individual clusters. And this is one example I'm working on, is named it the cosmic archipelago, because so there's a main Lyman alpha emitting galaxy, but then close to that one, there are some other ones within few hundred or 100 kiloparsec. But focusing on this main one, which spans more or less 6 kiloparsec intrinsically, and it's strongly magnified, so with a magnification up to 20, factor 20. This is how it looks like in rest frame UV with James Webb. This is actually, again, the halo news. What we see in the rest frame UV is actually that it's the stellar counterparts of Lyman alpha halo are simply these few spots here that if we zoom in into these squares, they are made of very compact sources. So if we measure the sizes of these sources and with the lens, we account for the magnification, we're reaching radii which are smaller than 10 parsecs. So again, we are really seeing individual clusters in this high redshift 6 galaxy, which, by the way, is something I would have thought when I was studying clustering in the nearby universe a couple of years ago. I wouldn't thought we would be able to see that with James Webb. And this is thanks to the magnification of the galaxy. And not only, so we can also see that in some of these clusters, we're seeing emission lines. So we have IFU cubes here. And that means they are very young, so 1 to 5 million years. In some other, we don't have lines, and these are probably older than 10 million years. So I mean, more or less what we see locally. So that they may have, within the same galaxy, they may have different ages. Star formation is taking place at different ages in different parts of the galaxy. Not only, so here I also wanted to show that within this same very small region, we can distinguish some, maybe it's not easy to see, but some different like cores. So there's a main core, which actually is not emitting, and a core next to it, which is highly emitting. So we're really seeing parsec scale details thanks to magnification. And why are they useful? So for example, to understand what the properties of galaxies, of galaxies we see at higher redshift. One example is ionization. So recently it's been suggested that low mass galaxies or faint galaxies, more properly, are efficient ionizers. So they would be the main responsible for reionization. And what this plot is showing is, so it is luminosity on the x-axis, and on the right we have faint sources, versus Xion, which is the ionization efficiency, more or less. So the ratio between the number of ionizing photons to the non-ionizing photons. And it looks like there's a slight increase, so that fainter sources are more efficient. But if we put in this plot the sources of the cosmic archipelago, we see that they span actually a lot of values. In particular, so there are some very efficient sources in the archipelago, but also in literature galaxies, which have this very extreme efficiency, which are consistent with actually, or comparable with the efficiency of individual, very massive star-forming class. I mean, 1 million year old clusters. This is from the BPAS models. So what we are seeing, the efficiency are seeing are really comparable with the cluster, suggesting that what we are seeing are either very massive cluster or a collection of individual clusters in some cases, in some redshift galaxies. And on the other hand, we are seeing also some non-emitting clusters. So what very low ionization efficiency means non-emitting clusters. So that may suggest enough mode of star formation, so that we are seeing the galaxies or the cluster just after they've been bursting. And this is particularly interesting. So we are seeing them in the archipelago because they are close by to our other emitting sources. But otherwise, these kind of sources are really are currently missing at all at redshift. So at redshift, currently the study is very much biased toward these extremely emitting galaxies. Second example I wanted to make is, or a second topic is about the search for metal poor systems. Here is a mass metallicity relation. Some redshift galaxies, or redshift is actually 0 to 10, more or less. They are more or less clustered here. Apart from these are actually, again, a lens source. So this lab one is the lens source studied by Jaros Banzella a few years ago. Again, very much magnified. If I put here the sources from the cosmic archipelago, they are clustered here at like almost 1% solar metallicity and very low masses. And again, it's interesting because it looks like in order to see the pockets of, in order to see metal poor system, we need to look for small pockets. In particular, many or some of these sources are not even the main UV sources I showed you before, but they are offset from the main UV sources. And we got the idea of the metallicity just because by looking with the IFU at these, at the main sources, we were able to see line emission in these regions. And then we also recognize that we got a counterpart in the rest UP. But again, this tells that it's very important to be able to see, to look at the faint and small scales in order to see, in this case, low metallicity sources. So to conclude, last example is this other galaxy I'm working on, Cosmic Gem. This is even at higher redshift, so 9.6. And again, I just wanted to show that, again, we see compact emission here, and it turns out that since it has a very large magnification, these are individual clusters, so actually sizes of 1 parsec, more or less, which are these color points here. And not only, I mean, they are individual clusters, but they are clustered with more than, I mean, 10 to the 5 solar masses cluster contained within a radius of less than 50 parsecs. So this is really something is not observed in the local universe. So something very dense. So very dense within this 50 parsec. And it looks like this suggests a very extreme star formation efficiency. So if we consider the local cluster mass function, so the local relation we know, it looks like either more than 100% of star formation is taking place of this cluster, or, I mean, in order to explain what we are seeing, it looks like at high redshift, star formation is tend to form more massive cluster on average than what we are used to see locally. And actually, this is the second time we are able to do this kind of trick that to see individual cluster at high redshift and be able to understand what's the efficiency of cluster formation, which is something done only at low redshift otherwise. And last, these clusters are not very young, and so we have IF data. We see that there are very faint lines, a little bottom break, and so it looks like this galaxy was like a factor 4 brighter in the past, like in 10 million years ago. And so this may be an example of one of the very bright and compact galaxies, sometimes called the blue monsters, just after it finished its episode of star formation. So then this work we are doing, but this again, it's interesting because what remains of these blue monster are very dense clusters. And these are my conclusion. I'm over time, I guess. I just want to say this, most of what I was showing, at least at the end, is work in progress. And there are new, especially James Webb programs, with new clusters, new kind of data. So I mean, a lot more. So we're just at the beginning. A lot more is coming now. And then there will be ELT coming soon, which will provide, again, a very small angular resolution, even without lens. So I guess we're really at the beginning of looking at cluster at high redshift. Thank you very much.
Thank you very much. Questions? Was that okay for the amount of work? And just a curiosity, sorry if I missed it. So when you show the cosmic archipelago, and you showed also the different emitting lines, like emission lines, sorry, in each of the JWST parts or IF parts. It's not clear to me if you have a single length image with multiple star clumps, or if you have 3 length images of the same clumps. That's just because I'm not familiar.
No, what I was showing was actually both. So because in the first image, what I was showing in the first image,
yeah, the first one
were different. So there were also
the next one.
Okay, because here what I'm showing, so whatever I show next is just this arc here. So it's a single image. So what we're seeing here are not multiple images, just part, I mean, different part of this single
so
line emitting galaxy.
So you have all of these clumps with different emission lines in a very small region of the source plane. So how common that is that these stellar clumps have such different properties in such a small region, therefore, let's say, in a standard?
Well, I have to say that most of the clumps here looks like they're very young, and the one at the top here is the exception. It looks like it's older, and so the scales here are more or less 6 kiloparsecs. So I mean, here to here it's 1 kiloparsec or so. So it's not. Okay. So the point is that the magnification is very stretched in this direction. So that's why it allows us to see these very small scales. But then, yeah, I mean, this whole arc is 6 kiloparsecs. So I mean, here we're taking, if we take these different parts, there's some difference. If we look at what I was showing here, so here actually we are within some at max 100 parsec. And yeah, we see that there are regions with different properties. I think it's not uncommon even at low redshift, even if it looks like most of, at least at high redshift, most of the cases we see either the galaxy is not clumpy and not emitting at all, or they are all very much subregion or very much emitting. But I don't think it's much uncommon. Then this core was particular because it was also very blue. So we also had this hypothesis that it could be a leaker. So it actually is very young, and we don't see the lines because it's leaking.
So you show the plot of where you have the star formation rate density as a function of redshift, and also, if I understand, the fraction of galaxies that are clumpy?
No, so I think if what you're referring to is like, let's say this one.
No, no.
Okay. So a function of clumpy galaxies was only this
Yes.
one.
Yes.
Okay.
So now the blue points is the fraction of clumpy galaxies.
Yes, exactly.
So how robust is the measurement at high redshift? And if it is robust, what is your interpretation of the fact that you have a smaller fraction of the clumpy galaxies with very high redshift?
I don't think it's very, very robust because this is HST. This is based on HST. So I don't think that above redshift 4, I don't think it's very robust. So there's been a more recent paper, I don't know, 2022 or 23, that was focusing on these like 2 to 5, I think, redshift range, and it was finding a flatter, and still a decrease, but a flatter decrease. I don't really, I mean, I think this should be redone. So this is something that with the statistical sample, we're starting to feel could be redone, but it's very time consuming. That's why we haven't done that yet. But yeah, because yeah, otherwise I'm not sure about the interpretation of this such declining clumpiness. The point I think is also that a redshift 6 and above, the galaxies basically, for what we see now with James Webb, are just a collection of 2-3 clumps. Part because if there's an older component, it would be even redder, and we are not seeing it. So this is debatable. But at some point, galaxy looks like that. I mean, they're smaller, they're less massive, and it looks like they're simply a collection of 2-3 clumps. And then those redshifts saying what if a galaxy, I mean, you don't see like a spiral galaxy with no clumps, and you can say, oh, this is not a clumpy galaxy, this is a clumpy galaxy. It's become even, yeah, it becomes very difficult to say this is a clumpy galaxy, this is not a clumpy galaxy. So I thought those high redshift probably is not even doable.
Very quick question.
No, very quick. Do they account for the reionizations? I'm sorry, I missed the first part of your talk. This galaxy has the UV budget is enough to account for the reionization, or you need, or I mean, they are not representative, or.
So what I was showing, I mean, the lens galaxy I was showing, I mean, we are not really focusing then. I mean, we're focusing on a few cases, and so not doing the entire function. I mean, so yeah, part of the sample wouldn't be part of this kind of scenarios. So I mean, it's related because it's been saying that this, if low mass galaxies are more efficient in ionizing, then you can rescale things, and you need less. Since you have a lot of low mass galaxies, then you need less reionization from the
So you have not
galaxy. But yeah,
escape fractions.
Okay, so we are a bit over time, so let's thank the speaker again. I will be told that at 5 there will be a meeting here for PhD and postdocs.
Yes, so we will talk about the like there will be some people from ADI that will tell